Yes, good morning all the students. Let me share the presentation. Can you see this?
Yes, ma'am.
Right. Okay, let's continue our fifth lecture under module 1 because we are left out with some topics which have to be covered under this lecture. So in the last to last session, we have seen how to understand about concept learning and how a simple concept learning task can be performed by a machine by taking help of an example of whether your friend will enjoy a water sport given some days climatic conditions as training experience to the machine. Now, when it is given an arbitrary day or when it is given a new day's data, it should be able to predict whether your friend will enjoy that particular water sport on that day based on his behavior with last few days provided as training examples on which the machine has learned, right? Now we have started about understanding concept learning as a search problem. Why? Because every concept learning has lots of hypotheses in the hypothesis space. Okay, so if you take this enjoy sport problem again, day 1 can be covered under one hypothesis, day 2 can be covered under one hypothesis, day 3 can be covered at another by yet another hypothesis, right? So there are lots of hypotheses which will cover each type of training example provided to the machine. Okay, now within all these hypotheses, the machine will try to generalize the hypothesis so that one hypothesis can cover lots of instances, because each time the machine can't generalize with respect to some 10 statements, right? Whenever you are asked to make a statement about some political situation in India, you will make 10 statements or one statement, right? And that statement you're making by learning from different states political scenario, correct? So you're making a general statement, one single statement there. In the same way, machine also will try to generalize the hypothesis so that it can cover multiple training examples. Okay, it can explain the behavior of multiple training examples, right? That is how the machine acts while learning. Okay, so that entire hypothesis space H is treated as having lots of hypotheses in it, and the machine tries to learn the most general hypothesis that best explains that particular problem at hand. Now again, sometimes not a single hypothesis will be enough in order to generalize. It may find out that 3-4 hypotheses will suit the data that is being trained on, right? In that case, 2-3 hypotheses will be used by the machine in order to predict something. Okay, it is not that always it comes with one single generalizable hypothesis. It may come up with the best suitable multiple hypotheses also, which can be used in order to predict a new data, predict about a new data point, right? So what it is trying to do here is, instead of considering 10 hypotheses for all the 10 training examples, means 10 hypotheses for all 10 sample points or data points, means the number of rows you have in the training set. Okay, now from that 10 training examples, it will not learn 10 hypotheses. It will try to generalize and minimize the number of hypotheses. Though it may not be equal to one hypothesis, still it will try to minimize the number of hypotheses considered by the machine in order to predict something after learning from the training examples. Understood? Now let us learn about the finders algorithm in order to find a maximally specific hypothesis. See, we are using the word maximally, means it should cover maximum number of instances of the training example. That hypothesis should be applicable to maximum number of training examples. Training examples means what? You have column 1, column 2, column 3 with an outcome variable, right? This is how you see your data point. And the training examples or rows are T1, T2, T3 and T4. I'm using a different alphabet here. Do not get confused. Before I used to use x1, x2, x3, and these sample points s1, s2, s3. Right? We can use any terminal, any representation, not a problem. Now I'm trying to represent the columns by using C and rows by using T, or training examples, or the rows in the training set I'm using T1 to represent them. Okay, now these are all the instances which will make the machine learn from those instances. Each is a row with some outcome variable yes or no in case of binary classification problem. Right now, the finders algorithm, or some algorithms what we are going to see in forthcoming sessions, we are trying to find, by using those algorithms, we are trying to find maximally specific hypothesis. Maximally means it should be able to cover maximum number of training examples. Say I have hypothesis H1 that is applicable to 3 training examples, and I have hypothesis H2 which will be applicable to the last training example. Means I'm making one hypothesis explain the behavior of multiple training data, multiple training examples, or multiple rows in the training set. That is called as maximally specific hypothesis. Okay, we are trying to find maximally specific hypothesis by using this find S algorithm today. Okay, that is very simple algorithm which we can easily understand. So in a previous session, we have understood how to treat concept learning as search problem. And we also saw how to compute the number of semantically distinct hypotheses that can be generated if each column is having certain number of categories. Okay, I'll ask you a question on this by the end of the class. So stay informed on that. Okay. Now we have also seen how to use this general to specific ordering of hypothesis by taking help of 2 hypotheses. Right? In this case, we understood that H2 is more general than H1. And for that, we have used a symbol called as more general than or equal to H1. Right? Because H1 is imposing more constraints, more rules, or more requirements, and H2 is imposing less number of requirements, we say that H2 is more general than or equal to H1. Got it? Now for that we have used this text, more general than or equal to. Now when we say given a hypothesis Hj and Hk, Hj is more general than or equal to Hk if and only if any instance that satisfies Hk also satisfies Hj, because Hj is more general than or equal to Hk. Right? This we understood in the previous class, and we have seen a formal definition for this relationship, and also with the help of an example by taking the instances in one figure and the hypothesis. And you observe that all the general hypotheses are towards the bottom of this hypothesis space, and all specific hypotheses are towards upwards, to the upward direction. Okay, because they specify more specific examples. They have lots of constraints imposed on them, whereas the bottom hypothesis have lesser constraints or rules imposed on them. That is why they are more general. They can cover more number of instances or rows in a training set. Okay, now let us see in detail, very slowly and clearly, what is this find S algorithm. Though these algorithms are not very efficient and they poorly cover lots and lots of scenarios, still I'm saying poorly cover means they don't cover lots of scenarios, they don't cover lots of problems, but still they can be taken as a baseline to understand the algorithms. Means they can be taken as the point to start from to understand other algorithms in machine learning. Okay, so this find S algorithm, candidate elimination algorithm, all these will help us to understand the basic idea, the basic notion of how this finding a specific hypothesis can be treated as a search problem, because you are searching many alternative solutions and you are finding the best solution available, or multiple best solutions available. Okay. Now let us proceed with understanding how to find a maximally specific hypothesis, okay, which can be used by the machine in order to predict for future data points, unseen data points. Okay. Now how can we use the more general than partial ordering to organize the search for a hypothesis consistent with the observed training examples? Okay, how can we use this idea of more general than partial ordering in order to organize our search space? Because our search space has lots of hypotheses. Our search space, hypothesis search space H, has lots of hypotheses. Now how to organize those hypotheses so that the final hypothesis or the final set of hypotheses will be consistent with the training examples. Means it should cover all the training examples. It should not leave out any training example, right? So how do you use this idea of more general than rule? Okay. Now one way is to begin with the most specific hypothesis in H. This is very important. You have to mention this when you are answering about this find us algorithm. You have to begin with the most specific possible hypothesis in H. Specific means always there is rule on every attribute. Rule on every attribute means lot of constraints on every attribute. Means your friend is not comfortable with any of the climatic condition. That is called as most specific possible hypothesis in H. Then generalize this hypothesis each time it fails to cover an observed possible training example. What do we mean by this? Say you have these attributes: sky, wind speed, humidity, and this is the outcome whether your friend will enjoy the sport or not, right? Now you have row 1, row 2, or day 1 data, day 2 data, day 3 data, and day 4 data, right? Now whenever you start with a more specific hypothesis, how will be your hypothesis? How does your hypothesis look like? You impose constraints on all the attributes. Means your friend is not comfortable with whatever is the weather condition on that day. He will not enjoy the sport. That is the most specific hypothesis. Having constraints on every possible attribute is called as the most specific hypothesis. Okay, so you need to make the machine start with this most specific hypothesis. Okay, now you see the first training example, that is day 1 data. Now day 1 data is sunny, wind speed is high, and breeze is strong. Now machine encountered a different set of values under these columns C1, C2, C3 other than this pi value. Means, and also remember, it is the outcome is predicted as S. The outcome is given as S. Means that is a positive example in which the machine is interested in. Okay, so it will now change all these pi symbols, that is your hypothesis H1. Now all these pi symbols are changed to whatever is given in the first training example, because you have to focus on the outcome. Only if the outcome is positive, only if the outcome is S, only in that example the machine will be interested. Remember, the machine is learning about a concept C. What is the concept? Whether your friend will enjoy the sport. It is S, only then that day's attributes will be taken. Okay, so when it is trying to learn the concept C, it will treat only, it will consider only the positive examples, or it will consider only the members of the hypothesis, that are this S labels. Okay, so because this outcome is S, it will take sunny, it will take high and strong, right? This is hypothesis H1. Now let us assume second hypothesis, second training example also, given the label as S. Now in this case, instead of sunny, say the training example has cloudy under sky attribute, and wind speed is same, high, and humidity is high and wind speed is strong. Both are same. Because both are same, observe this H1 already covers this attribute and this attribute value, high and strong. But it encountered a new attribute value under sky. So what it has to do? It has to generalize that particular value. So what will be the next hypothesis now? This will be more general hypothesis. You replace sunny by question mark. Why? Because sunny is now changed to cloudy in the second day's data. So you are making a hypothesis which can cover sunny as well as cloudy. Means you are making your hypothesis more general. So in that case, it is having less constraints. That is why you are using question mark. Then the other two values you can use as it is, high and strong. Right? Now you're going to the third example. Cloudy and this humidity is high and wind speed is moderate. And still your friend will enjoy the sport. The outcome variable is S. How do you generalize now? What will be your third hypothesis? In the initial case, it is already generalized. In the next case, it is same high. So you can keep the value as high itself. And in the last case, it has changed. It has changed to moderate. In the initial cases, it is strong, but later it has changed to moderate. Means this new hypothesis should cover both the conditions, strong as well as moderate. So this will become again question mark. Okay, and you're modifying the hypothesis, or the machine is modifying the hypothesis only because the outcome variable is S. Now, in the last case, say the outcome variable is no, and here it is cool or rainy. Take the sky as rainy, and C2 you can take it as high again. Let it be high, humidity, and C3 again moderate. Let it be. Okay. Now C2 value didn't change, so leave high as it is. C3 value didn't change, so you can keep your previous generalized value as it is, and the first one also as it is, but leave about that. Leave about modifying the hypothesis. You see what is the outcome. The outcome is no. The label is no, and machine is not interested in negative examples. So it will keep the hypothesis as it is without making any changes. Though here instead of high, if it is given as low, still this will not be generalized in hypothesis H3. Why? Because the outcome label is no. Machine will not be interested in the outcome label. Machine will not be interested in the training example where the outcome variable is no, because it doesn't come under the concept which it is interested to learn, right? So the final hypothesis can be this H3 itself without modifying. Because of this last day's data, you will not modify because the outcome is just zero. The outcome is no. Okay, so the final hypothesis can be best hypothesis that is suitable and covers all your training examples D1, D2, D3 and D4. whichever are the training examples given in the training set. This H3 covers all those training examples. So this H3 is your most optimal hypothesis which covers all the training examples, which is a best fit to all the training examples given. Okay, so this hypothesis here, hypothesis space here has H1, H2 and H3. From that, H3 is being taken because it covers all the training examples. H3 is the best fit hypothesis. Okay, that is what is done by Finder's algorithm. Now let us see in terms of a formal flow of instructions. Okay, now what is the first step? Initialize H to the most specific hypothesis in H, means you are taking it as pi. This is the most specific hypothesis where all constraints are imposed. Okay, so that H will be initially H is initialized with pi. Okay, for all the attribute values. Now, what is the second step? For each positive training example, remember this step. Positive training example, only when the training example is positive, means only when the label of that example is S. For each training positive, for each positive training instance X, what has to be done? For each attribute constraint AI in H, means this attribute AI, A2, A1, A2, A3 and A4. Okay, for each attribute constraint AI in this hypothesis H, that is the base hypothesis H, if the constraint AI is satisfied by X, means if there is again a pi, leave it. But if it is not pi, put that attribute value into the hypothesis. That is what we mean by this line. If the constraint AI is satisfied by X, then do nothing. If there is pi, do nothing. If there is not a pi, put that value. Okay. I am repeating again. If the constraint AI is satisfied by X, means if there is again a pi in the training example also, do nothing. Don't replace it. But if there is another example other than pi, means there is sunny or there is cloudy, in that case, put that particular attribute value in this place. Because we encountered sunny, will replace pi with sunny now. Right? Now I'll repeat this again. If the constraint AI is satisfied by X, means if the new instance again encounters a pi value, do nothing. But if it doesn't encounter the same value, then you have to replace that new attribute value to cover this pi. Means this pi should be replaced by sunny now. What you're doing on the else case, else replace AI in the hypothesis H by the next more general constraint that is satisfied by X. Okay, so what is the more general constraint it has come across now? It is sunny. It is not pi value. Means the training example doesn't allow any value. It just allows sunny so far. Okay, so sunny is replacing this pi. Now this has to be repeated. Did you see? For each is given here. For each means this is iterative process. It has to be repeated again and again until the hypothesis covers all the training examples. Okay, finally output the hypothesis H. In our previous example, what I have shown, this hypothesis H3 is the final hypothesis, that is output. Why? Because that is the most general hypothesis which covers all the training examples D1, D2, D3 and D4. Did you understand? Okay. Now can you start working out on this training set given? Again, we are taking the same old training set whether your friend will enjoy a sport or not, given some days weather conditions. On those days, whether he enjoyed or not, machine will learn from that data, and when a new day's data is given, it will try to predict whether your friend will enjoy that water sport on that particular day or not. Okay, now I'll not show you the steps that have been approached by using this algorithm. Just try to start with the most specific hypothesis. I'll keep this slide for 5 minutes. Take a pen and paper and start with the most specific hypothesis. And when day one is encountered, how the hypothesis changes with day 2 data, with day 3 data, and day 4 data, how the hypothesis changes. Observe the attribute values carefully and work out and let me know what is your final hypothesis. I'll give you 5 minutes for this and I'll randomly call some name and you have to answer. Make it fast. The time starts. Take 5 minutes. Start from the most specific hypothesis. Apply this finders algorithm to find the more general hypothesis that covers all the training examples. If you work out this one, when I show you how the steps are taken, you will easily understand whether you have done correctly or not. So I'm assuming you have started working on it. Yes or no? Surya, you are ready to answer?
Not yet, ma'am.
Let me give you some more days data. It is very small, I think. Let me give you some other data. Find out the more general hypothesis which covers this 5 and 6 example days data also. Air temperature is warm. It is high. Slow. Forecast is random. Let us take it as random. Okay. And the outcome label is S. Let us still take the sky as cloudy. Air temperature as warm again. Humidity is moderate. Wind is slow. Water is say steamy. Let us just take it, though it is not so meaningful, take it as steamy. And forecast is again change. And the outcome is no. Okay, now take make a hypothesis, generate a hypothesis that covers all these 6 examples, not only 4 examples. And when I pass through the slides, I may not be able to come to this example again. So keep me informed about those two new examples, okay? Some of you have to read out whether they have changed or not for me when I'm working out with the problem. Sridhar, be ready with the solution. I'll ask you to present. You can just start presenting by focusing on your paper. Apurva from lateral entry batch. All names whom I'm calling, be ready. Sadev, Nazma, Paresh.
Doing, ma'am.
Yes, yes. No, I'm just calling the names so that you'll be ready. Of course, Divyesh and Murugesh can do it very well, right? Because they stayed connected to the class even after the class ended yesterday. I think they can do it very easily.
Trying to do, ma'am.
Hmm. Carry on. Bindu, Mutamesh, you are there? Whoever completed, you can ask me to allow them to present. I'll stop sharing my screen. Let me see who will do it first.
Ma'am, I haven't written, but I can tell the answer.
Who is this?
Paresh, ma'am.
Paresh, yeah.
So, final hypothesis will be question mark, warm,
1 second.
then
Question mark.
warm,
Yes.
then question mark, question mark, question mark, question mark.
Question mark. Question mark. Question mark.
Question
And
mark. Question
question
mark itself.
mark. Yes. Last one.
Question mark itself, ma'am.
All are question marks.
Yeah, ma'am. Just the second one will be warm.
Second one will be warm.
Yeah, rest
Yes.
all are changing.
Yes, very good, Paresh. Can anybody else tell me what is your answer? Good, Paresh. I have a doubt why you didn't change cold for air temperature. From
Ma'am,
warm, it
because
has changed. Wait, let
be,
me ask the question so that the context will be clear to other students.
sure.
I, I'm having a doubt with your answer. Why? Because air temperature initially it is warm, but in one training example it has changed to cold. But why didn't you replace warm with a question mark when next different category is encountered.
Ma'am,
Yes,
because
ma'am.
it's a negative
It's a negative label.
outcome.
No.
Yeah.
Right? So you didn't make any changes.
Yeah, so I
Okay.
ignored the whole instance.
Very good. Yes. Sridhar, can you tell me your answer?
Yes, ma'am.
Hmm. Tell me what it is.
Ma'am, first question mark
Okay.
and then warm.
Warm. Okay.
In humidity, last one, what is this?
Last one is moderate.
Okay.
This one you want?
Yes, ma'am.
Moderate.
Ma'am, give me 2 minutes, ma'am. I will
Okay.
give.
Yeah, yeah. Anybody else is ready? Now I'm changing the 6th day's data. I'm removing this 8 temperature warm and I'm giving it as hot. Okay. And I'm taking the label as S. Now tell me the new generalizable hypothesis. Other students.
Everything will be
Everything will be question mark. Who is this?
Tanuj.
Tanuj. Everything will be question mark. Why? Because hot is a new attribute value that is encountered by the machine, and also the outcome variable for that day's data is S. So it will generalize that 8 temperatures data or 8 temperatures value also to question mark. Got it? How many of you got the correct answer? After changing this, all will be question marks itself, so that that hypothesis covers all the training examples given. How many of you got that? You can just say yes in the chat box. I'll see it after the class and feel happy. Okay, shall we proceed now? For if at all any students didn't understand how to do this, let me explain you stepwise. Okay. Now see the first step. What is the first step in finders algorithm? Take the most specific hypothesis, right? So the first step of finders algorithm is to initialize H. You're taking H to the most specific hypothesis in the hypothesis space capital H. So what is the most specific hypothesis? Whenever I say most specific, you have complete constraints imposed on that hypothesis. Means no value is allowed under the attributes. So initially it is pi. Still the machine hasn't started learning. So it doesn't have any idea about your friend's preferences to enjoy a water sport. Preferences means his most friendly climatic conditions. The machine doesn't know. So initially its knowledge is zero about your friend's interest. Okay, in that way also we can understand. So whenever a machine starts to learn, initially its knowledge is zero, or it will start with a specific hypothesis. That is, every attribute value is replaced with pi. Pi means null. It doesn't know anything. Let us go to the next step now. What is step 2? As the hypothesis is too specific, none of the pi constraints in H are satisfied by this example, right? So whenever you have the first day's data, whenever the machine encounters this first training example, This entire row is a training example. Now, whenever this first day's training example is encountered, it started gaining knowledge about your friend's preference to enjoy a water sport. And it is, the outcome label is S, means this is the concept it is interested in. Because your friend is enjoying water sport on that particular day, it is interested to learn, the machine is interested to learn what are those climatic conditions in which he enjoys the sport. So the machine starts learning. So what is the first value encountered for sky? Sunny. So pi is replaced by sunny. What is the A temperature value? Warm. So pi is replaced by warm. Pi is replaced by normal, strong, warm, and same. Right? This is the modification for your hypothesis. So what the algorithm says is, if it again encounters a pi, if it doesn't have any additional knowledge about that particular attribute value, let it be pi itself, do not make any change. But if it gains some additional knowledge about the preferences of that of your friend, then immediately that new knowledge will replace the old knowledge. So pi means having no knowledge is now replaced by on the day when the sky is sunny, air temperature is warm, humidity is normal, wind speed is strong, water is warm, and forecast is throughout the day the weather doesn't change. In that particular day, your friend will enjoy the water sport. Okay, that is the new hypothesis. Now this hypothesis covers day 1. This hypothesis covers the training example 1. Do you agree with me? Yes or no? Is it very difficult for you to reach the microphone and unmute it and say yes or no when I'm shouting on the other side? Lazy students, talk something.
No, ma'am.
Yes, ma'am.
No for what and yes for what? Please make it clear. You're not lazy, no, right?
Yeah, not lazy, ma'am.
Okay. S is for my question, right? Okay, you give
Yes,
your
ma'am.
answer, I'll match the following to the question. Okay. So sunny, warm, normal, strong, warm, and same will cover the first training example. Now, shall we proceed further? Now, this H, yes, this H is still very specific. It covers only first training example. We do not know whether it covers other training examples. Let us see. Okay, it asserts that all instances are negative except for the single positive training example we have observed. So it has learnt about only day 1 data, and for all other instances of those attributes, it may treat it as negative example because it hasn't encountered, means it hasn't come across those days data still. Okay, so the second training example, also positive in this case, forces the algorithm to further generalize H. What is the next training example? Sky value didn't change. Air temperature also didn't change, but humidity changed from normal to high. Because training example 2's humidity changed, it has to cover normal as well as high. Means it is imposing lesser constraint now. It is okay with normal as well as high. Your friend is okay with normal as well as high. So you don't impose any constraint on this humidity according to the training examples learned so far. So replace normal with question mark now, indicating that it is more general now, indicating that it can cover the second training example also. And wind speed, strong, warm, and forecast. All this didn't change. So keep them as it is, strong, warm, and same, right? Now, upon encountering the third training example, in this case, a negative example, see? Means it is not a member of the concept. The machine will not be interested in negative examples or negative classes. Okay, this S is taken as a positive class and no is taken as a negative class. Now, while learning a concept, your machine will not be interested in a negative example. That is no. So, when it sees rainy, that is the sky the sky condition changed, still it is not replaced. Sunny will not be replaced and warm will not be replaced, and question mark lies as it is. Strong, warm, same. Though there is change in the forecast, still it is not replaced. Why? Because this is a training example and machine doesn't want to learn anything from a negative member or a negative concept, means which is not a member of the concept, right? So it doesn't make change, to the hypothesis in this third step. That is repetition of your second step itself. It doesn't make any change. Why? Because it didn't learn anything new, because it is a negative example. Okay, now let us go to fourth day's data. Now fourth day's data is again a S. Then machine will be interested in that fourth day's data. So what it takes for sunny, no change. So it keeps sunny as it is. Now A temperature, no change from warm. That is previous S example, it is warm. So no change in the warm condition, it is kept as it is. Question mark is left as it is, and strong didn't change, so it is left as it is. Now warm is changed to cool now, so it is replaced with a question mark, means you are making your hypothesis more general now. It can cover any value for humidity and it can cover any value for water temperature, right? And the last one, though the temperature is same throughout the day or the temperature changes, still your friend is ready to enjoy the water sport. So make your hypothesis more generalizable. So it is again question mark. Okay, so this is your final hypothesis. Sunny, warm, question mark, strong, question mark, and question mark. Now I have given you some 2 extra days example, right? 2 extra days training data. In that case, sunny is changed, so you replace with a question mark. Again, strong is also changed, so you replace with a question mark. So your final hypothesis will be question mark, warm, question mark, strong, question mark, and question mark. This will be your final hypothesis. I hope all the students got this answer. And when I further changed 6th training examples data from warm to hot, then this also will be replaced by question mark if the outcome variable is S. If the outcome variable is no, then the machine will not be interested in that training example. Okay, this is how we can understand this find S algorithm. Now let us understand it with respect to a figure so that it will be more clear for us. What is the time, students?
9:23.
9:23. Okay, I'll quickly end this explanation. See, in this particular figure, this instances X set will have here X1, X2, X3 and X4 given to us in the training set, right? So this is a positive example. X1, X2 and X4 are positive examples and X3 is a negative example. Okay, now let us see the hypothesis space. Initially, H0 is the most specific hypothesis and H1 is a transition from that specific hypothesis. So it is still more specific. So it lies on the top. Now, when H2 is H1 is modified to H2, it becomes more general because we have replaced normal with a question mark. So H2 comes towards bottom of this particular hypothesis space. Even H3 also is more general. So both of these are here. Did you observe one thing? The arrows are being pointed from more general to more specific. From more general towards more specific. Okay, towards the top part of the hypothesis space. Now, whenever H4 is taken, that is more general than H1, H2 and H3, right? Because we have lesser constraints on that. So it is at the bottom part. And here these lines represent H1 will cover X1, H2 and H3 will cover X1 as well as X2 examples, and H4 will cover X4. Okay, all this hypothesis covers all the training examples except H3. Except X3. Why? Because X3 is a negative example. The machine will not learn anything from that. No useful information will be provided by X3. That is day 3 data. Okay, that is how we can understand. Now the key property of the finders algorithm is that for hypothesis spaces described by conjunctions of attribute constraints, conjunctions means and, sky is this, and a temperature is this, and humidity is this, means you are giving constraints as a conjunction and you want all of them to be true. Okay, that is the final label to be yes or no. Okay, now find S is guaranteed to output the most specific hypothesis within H that is consistent with the positive training examples. Okay, so the find S algorithm's objective is to find the most specific hypothesis within H that is consistent with all the positive examples that are given in the training set. Now, its final hypothesis will also be consistent with the negative examples automatically. Though it is not interested to learn the negative examples, the final hypothesis will automatically cover those negative examples also, provided the correct target concept is contained in H. But you have to make sure that the correct target concept is learned, and provided the training examples given are correct. There should not be any noise in the training examples. If there is any noise or outliers in the training example, then automatically that will deviate your hypothesis. You may get some wrong hypothesis which may not cover that noise in the training data. So you should make sure that your training data doesn't have any noise or outliers or missing data, so that your machine will efficiently learn. Now, what are the unanswered questions by this finders algorithm? Have the learner converged to the correct target function? Means whether the final hypothesis covers all the training examples or any training examples has missed out, it will not be indicated by the finders algorithm. Okay, so we will not know whether there is a single hypothesis or multiple hypotheses, and whether all of them are covering the training examples. Means all training examples will be applicable under that those hypotheses, final hypothesis or not. It is not made sure by this finders algorithm. And why prefer the most specific hypothesis? Why not more general hypothesis? When you're finding out more general hypothesis, can you decide that that is the most general hypothesis? And why to prefer more specific hypothesis when general hypotheses are available? That is also not answered. And are the training examples consistent? Are the training examples not having any noise or outliers? That also can't be detected by this finders algorithm. Finders algorithm can't detect noise in the training examples or outliers in the training examples, which will deviate the hypothesis, which will mislead the selection of the hypothesis by the machine. And what if there are several maximally specific consistent hypotheses? Say there are 5 best solutions or 10 best solutions. If there are multiple best solutions, what would be the final generalizable hypothesis? That also can't be determined by finders algorithm. Now in the next coming sessions, let us understand about version spaces, and the most important, though it is not very efficient, but still it serves as a baseline to understand other algorithms, candidate elimination algorithm, that we are going to see in the next class. Okay. Because of time constraint, let us not go for the quiz part, and I expect some best question from the students in the next class. Student who answers the best, who asks the best question, and student who answers to that question also will be given marks. Okay, this will happen in the next class. Any doubts still here, students?
No, ma'am.
Okay, then meet you in the next class.